In this episode, we're going to make sense of several security devices that get mentioned constantly in cybersecurity conversations, and we're going to do it in a way that keeps the limits just as clear as the benefits. Beginners sometimes hear words like firewall, intrusion detection, and intrusion prevention and assume these tools create a kind of invisible force field around the network. In reality, these devices are powerful when you place them correctly, configure them thoughtfully, and understand what they can and cannot see. Firewalls decide what traffic is allowed to pass. Network intrusion detection systems watch traffic and raise alarms, and network intrusion prevention systems go one step further and try to stop malicious traffic automatically. Each one plays a different role, and using them correctly is mostly about matching the device to the problem you're trying to solve. We'll focus on high-level mechanics, where they belong in a defensible architecture, and the common misunderstandings that cause organizations to overtrust them or misplace them. Let's begin with the simplest and most familiar concept, the firewall. A firewall is a policy enforcement point that examines traffic and decides whether it should be allowed or denied based on rules. Those rules often consider things like source, destination, port, protocol, and sometimes application characteristics, depending on the firewall's capabilities. The firewall is most effective at boundaries, where it can control the flows that cross from one zone to another, such as between the internet and an internal network, or between a user zone and a server zone. A firewall cannot magically make an insecure service safe, but it can reduce exposure by limiting who can reach that service. It can also reduce lateral movement by preventing unnecessary internal paths. The core value is that it turns a messy set of possible connections into a smaller, intentional set, which is both safer and easier to monitor. A key idea for beginners is that firewall rules are statements of intention, and they should reflect real business needs rather than convenience. When rules are broad, like allowing any internal device to reach any server on many ports, the firewall becomes a pass-through device rather than a control. When rules are narrow and specific, the firewall becomes a strong boundary that shapes how the network behaves. Firewalls also create valuable logs because each decision is a signal about what tried to happen and whether policy allowed it. That can support investigations, especially when you see repeated denied attempts that suggest scanning or brute force activity. But the logs are only meaningful if the policy is meaningful, because if everything is allowed, there are no interesting decisions to record. So using firewalls correctly begins with designing zones and then enforcing least privilege pathways between them. Now let's talk about network intrusion detection systems, which are often abbreviated as NIDS. The core function of a NIDS is to observe network traffic and generate alerts when it detects patterns that look suspicious or malicious. It does not typically block traffic by itself. It is more like a security camera that raises an alarm rather than a locked door. A NIDS can look for known attack signatures, such as patterns associated with particular exploits, and it can also look for anomalies, such as unusual traffic volumes or unexpected protocol behaviors, depending on the system. The benefit of detection is that it can spot threats that pass through allowed pathways, like an attacker using a permitted port for malicious activity. This is important because firewalls are not content judges by default. They are primarily policy enforcers, so malicious traffic can still flow if it uses allowed paths. A NIDS adds another layer by paying attention to what the traffic appears to be doing. Placement matters a lot for NIDS because it can only alert on what it can see. Putting a sensor in the wrong place is like installing a camera facing a blank wall. A common and effective placement is at a boundary where important traffic concentrates, such as between the internet and internal networks or between major internal zones. Another useful placement is near critical assets, where you want high-quality visibility into traffic targeting sensitive systems. The challenge is that modern traffic is often encrypted, which means the NIDS may see the connection metadata, but not the content of the session. That does not make NIDS useless, but it changes what it can detect, often shifting emphasis toward patterns like unusual destinations, protocol misuse, or timing anomalies rather than payload signatures. Beginners sometimes assume a network sensor can see everything inside traffic, but encryption reduces that, and you must plan for it. A network intrusion prevention system, abbreviated as NIPS, builds on the detection concept by actively stopping or interrupting traffic that matches known bad patterns. If NIDS is a camera and alarm, NIPS is more like an alarm with an automatic lock that tries to stop the intruder. This can be valuable because it can block exploit attempts in real time, reducing the chance that a vulnerability becomes a breach. However, prevention brings risk. If the device misclassifies legitimate traffic as malicious, it can disrupt business operations. That risk of false positives is one reason many organizations deploy prevention cautiously, especially on traffic paths that are critical to operations. A NIPS is often placed inline, meaning traffic must pass through it, while a NIDS is often deployed in a way that observes traffic without being in the direct path. That physical and logical difference is part of why prevention is more sensitive to performance and accuracy issues. One of the most important real limits to understand is that these devices do not replace secure systems, they complement them. A firewall cannot fix a weak password or an unpatched vulnerability. It can only reduce who can attempt to exploit those weaknesses. A NIDS cannot detect what it cannot see, and it can miss attacks that do not match its detection methods. A NIPS can stop known patterns, but it can struggle with novel attacks, encrypted payloads, or traffic that looks legitimate on the surface. Attackers also adapt, using techniques that blend into normal activity or that leverage allowed protocols. This is why you hear about breaches that happened even though an organization had firewalls and intrusion detection. The presence of these devices is not the same as effective use, and effective use depends on policy design, placement, tuning, and ongoing maintenance. Another limit is that these tools can create a false sense of security if people treat them as an excuse to keep networks flat and permissive. If everything is reachable, detection becomes harder because there are too many pathways and too much noise. Segmentation and choke points make security devices more effective because they reduce the traffic the devices must interpret and they align observation with meaningful boundaries. For example, a firewall between a user zone and a server zone can block unnecessary access and also provide clearer logs about attempted violations. A NIDS watching a boundary between zones sees more concentrated, relevant traffic than one watching a chaotic flat network. This is a key design insight. Tools work best when the architecture supports them. A monitoring-ready architecture is one where security devices see the most important traffic, not just random traffic. It's also essential to understand the problem of false positives and false negatives, because they shape how these devices are trusted. A false positive is an alert or block that identifies something as malicious when it is actually benign. A false negative is a missed detection, where malicious activity happens but the device does not alert. Detection systems always balance these risks, and the balance depends on tuning and context. If you tune a system to be very sensitive, you may get lots of alerts that overwhelm defenders and cause them to ignore real problems. If you tune it to be too quiet, you may miss important events. Prevention systems face an even sharper trade-off, because blocking legitimate traffic can cause immediate business impact. This is why mature security teams treat tuning as an ongoing process rather than a one-time setup, and why they prioritize high-confidence detections on high-risk paths. Another real-world challenge is performance and scale. Firewalls and inline prevention devices must handle traffic volumes without becoming bottlenecks, especially in busy environments. If a device slows down traffic too much, people may bypass it or disable features, which reduces security. Even detection systems can struggle if they must analyze very high-throughput traffic with deep inspection, especially when encryption reduces what can be inspected and increases reliance on metadata analysis. This doesn't mean that tools fail. It means you must design around capacity, choose placement wisely, and prioritize the most valuable traffic for inspection. A common beginner mistake is assuming you can simply turn on every feature everywhere. In reality, you often choose where you want deep inspection and where you want lighter monitoring based on risk and feasibility. Security is about smart coverage, not maximal coverage in one place. It's also worth noting that attackers can intentionally try to evade network detection, not by hacking the tool, but by shaping their behavior. They may move slowly to avoid triggering thresholds, use legitimate services to blend in, or rely on encrypted channels that reduce payload visibility. They may also compromise internal systems, and then use internal trust pathways, where traffic appears normal because it uses accepted protocols and ports. This is why network tools are only one part of the picture and why endpoint and identity signals are so important. A NIDS might see that a connection occurred, but an endpoint might reveal that an unusual process initiated it. A firewall might show that a connection was allowed, but authentication logs might show that the user identity was unusual. The real defensive strength comes from correlating these perspectives, not from expecting any single device to be perfect. As we wrap up, keep the roles and limits clear in your mind, because that clarity will help you avoid common misconceptions. Firewalls enforce policy by allowing and denying traffic at boundaries, and they are strongest when segmentation makes their rules meaningful. Network intrusion detection systems observe traffic and generate alerts, but their effectiveness depends on what they can see, which is affected by placement and encryption. Network intrusion prevention systems can block malicious traffic, but they must be used carefully to avoid disrupting legitimate activity, and they still cannot stop everything. These devices are tools that amplify good architecture and good policy, not substitutes for them. When you understand their real limits, you can use them as intended, building layered defense that reduces exposure, increases visibility, and makes attacker movement more difficult. That is what it means to use network security devices correctly in the real world.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.